is that? Let's try.
Too many.
Is it, which one is it? Is it this one? Which one is the stream direction?
Oh, I don't know. It's not letting you start.
All right. Orientation is locked, but I don't want to.
I would just do vertical.
Okay.
Don't allow.
All right.
How's the new venture going? Good? Yeah.
All right. All right, we're having tough technical difficulties here. Woo. All right, so. All right. I think we're live. Hope we're live. We are? Okay. Right, quick introduction. Thank you all very much for coming. Beautiful house. Yeah, it's my pleasure to introduce this group, Sigma3. I don't know why they didn't call themselves the principal stresses, and one could have been Sigma1, one could have been Sigma2, one could have been Sigma3. The engineers, I'll get that. Everybody else is like, what's it? Thanks a lot for my colleagues on the parts board. It's great to have the clients here for this presentation, and I'll turn it over to Steve.
So as Dr. Page mentioned, we are Sigma3. This is our senior capstone presentation, and our project was the Civic Park Lagoon restoration. My name is Taylor Hines, and I am the project lead.
I'm Kirk McCarlin, and I'm the technology lead.
So to start off, we have an aerial view of San Angelo. This red circle right here on the screen is where our project location is at in San Angelo. We're located at 2 South Park Street, and our entire project is going to be this entire area that's highlighted in blue. So for the park has been used for festivals, weddings, engagements, and educational purposes. It has been used a few times for San Angelo Independent School District for the kids to learn about gardening. It also has the largest community involvement, being the second oldest park in San Angelo. And then we just have some photos here of some festivals that have happened at Civic Park, as well as some engagement photos as well. So as of right now, the lagoon has a bunch of trash, sedimentation, and erosion damage. The lagoon was created with the hope that it would become a community pillar and a community hub. But given the current state of the lagoon right now, that's not currently possible. We want to make the lagoon a pillar and a hub for the community. We want it to be where San Angelo natives can go and hang out, as well as tourists as well. So the purpose of our project mainly is to restore the lagoon. And in order to do so, we will be improving the stormwater runoff quality. We will plan on reducing the city water usage for irrigation. We want to maintain the aesthetics of the overall park, and we want to improve the system resiliency.
So for the existing system layout of this lagoon, we have 2 main water runoff inlets into the park. One is on the north, where water is entering this detention pond just south of Central High School, where it then flows through the West Harris Avenue culvert and into the pond system. Another is on the west side of our park, where it flows through the North Park Street culvert right here and into our system as well. This water continues down into a collection area here, where we have an actual pond storage capacity of 2.5 acre feet. All an acre foot is like, imagine an acre acre plot of land with a foot of water on top of it. So just that 2.5 times is what we can store in there. Then any excess amount of water can flow through this existing overflow culvert into a debris basin that's just alongside the river. The debris basin is outlined by a gating wall to prevent any of that debris actually entering into the river. But overall, the system is not working as it is intended. On the south side of our park, we have a concrete dam that has tons of water seepage in its fish. To prevent any water from actually, or debris from flowing through that concrete dam and into the river, at some point, a gated wall was installed right in the middle of the pond, just to prevent any of that debris from actually flowing through there. So, but that has also failed. That's just due to an excess of sedimentation buildup, debris collection, and everything else with erosion. And then underneath the pond is a concrete liner that is also eroded away and led to that increase in sedimentation buildup throughout the pond itself. And then outlining the entire lagoon is a stone masonry retaining wall, which is also completely eroded.
So for our scope of work for this project, we developed conceptual hydraulic designs. We developed a stormwater reuse system, and then we developed conceptual design recommendations for the dam and the gating wall.
So to start off this project, we started with the goal of trying to retain as much water as we could inside this pond itself. However, as we progressed through that hydraulic analysis, that goal changed a little bit. So this process included site delineation of our drainage area, the creation or the calculation of our peak stormwater runoff, how that peak stormwater runoff looks inside the existing system, and then a design of a new hydraulic proposal. So for our site delineation, we used ArcGIS Pro, utilizing a digital elevation model. And what that resulted in was this image here on the left of our watershed, and everything in that gray area is the watershed itself. This watershed has a total area of 510.6 acres, which is a little bit larger than what we were expecting it to be. This was then broken into 3 subcatchments: the north, the west, and then the park itself, where the north being our largest subcatchment flows in from the north side of the park through the West Terrace Avenue culvert, and then the west flows through the North Park Street. So to calculate the peak flows from these catchments, we had to use the SCS method because our total watershed area is greater than 510.6 acres, or greater than 200 acres. And we had to use HEC-HMS as our tool. All the inputs for that were found using the ArcGIS Pro software. And then we modeled the 100-year, 50-year, and 2-year storm events using precipitation data found from NOAA. And the result of that is this 100-year chart shows that for the north catchment, it has a total water accumulation of 225.1 acre feet. From the west, we get 30.1, and from the park itself, it has a total water accumulation of 1.3. Now, as a pond's total, as a total collection point of all these catchments, we have 256.6 acre feet. So if you recall from earlier, we can only retain 2.5 acre feet. That is roughly 1% of the total water accumulation from that 100-year storm event. So now this project has shifted from how can we retain water inside the lagoon to how can we keep water out. So the main focus of this point was for that north catchment, where we have that 225, the greatest water accumulation of all the catchments. So let's try and look at where that enters into the lagoon itself, which is over on the north side, where it has that during that peak flow, we have 552.1 cubic feet per second entering this existing detention pond just south of St. High School. And then as it tries to flow through this West Terrace culvert, it gets backed up. It can't flow fast enough, as shown in this hydroflow model, and then it all accumulates inside this detention pond, possibly overflowing the road or backflowing into the high school. So, to fix this, what we propose is adding 2 new culverts. One, Divergence 1, which diverts water from the detention basin into the river directly. And then as the rest of the water flows to the West Harris culvert, there's a second culvert, diversions 2, where as that water collects on the north side of the pond, any excess can flow through the diversions 2 culvert and into this debris basin. The remaining water flows in and it intersects with the west and park catchments where any excess water greater than that 2.5 storage will overflow through the overflow culvert also into this basin, and then overtopping as it flows down and overtop a proposed conceptual overflow dam. Here's just a side profile view of what this looks like. So as you can see on the left side over there, we have that detention basin with that divergence 1 culvert, where as water collects, it starts to rise in there. It can be diverted to the river through that culvert. One thing we can note is that the divergence 1 culvert is actually higher in elevation. The inlet elevation is higher than the inlet elevation for the West Harris Avenue culvert. And that's just so that we want the low flow events to still flow into the pond and restore the storage that's in there. But during those high flow events, like the 100-year or 50-year, it can exit through that divergence culvert. And then following along, as it enters into the pond itself, any excess water that accumulates here can also flow through the divergence culvert 2, and then continuing on again, any excess water from the other catchments can also be overflowed through the existing overflow culvert, and then a new proposed conceptual dam site. So for diversion culvert 1, we suggest a 2-barrel 4x4 box culvert at an inlet elevation of 1822 feet. This is 3 feet higher than the inlet elevation for the West Harris Avenue culvert. And then for the diversion culvert 2, we suggest a 1-barrel 3-foot diameter concrete circular culvert. So going back through and modeling how these look at hydroflow again, as you can see from earlier, for that West Harris Avenue culvert, it was overtopping the road during that 100-year storm event. But now we're keeping water levels below the roadway level, and that's at flow of 200 cubic feet per second. And then for the diverging culvert 1, it's also keeping water levels below the embankment, and that's at a flow of 350 cubic feet per second. We have one utility conflict with divergence 1, and that is a sanitary sewer that runs just parallel to the river, and it intersects with our divergence culvert right here. So we ended up getting this plan set for the sanitary sewer from the city, and what it showed is that our elevation for the divergence 1 culvert is coming in below that sanitary sewer. So what we propose is just using, during any construction of this culvert or any excavation, there would have to be a cross beam and some straps just to give that sanitary sewer some extra support. And what's kind of interesting about looking at this sanitary sewer plan set is that whenever it was constructed, they actually filled all of this in right here. What used to be like a channel where water used to run. So in a way, by putting this divergence 1 culvert, we're just restoring back to what had already happened and occurred naturally over time. And then for the modeling of divergence culvert 2, it is flowing at a rate of 70 cubic feet per second and still keeping water levels below that embankment between the pond and the river. Energy dissipation, right now with this new model, the West Harris culvert has an exit velocity of around 12.5 feet per second during that 100-year storm event. And what we suggest is retrofitting roughness elements into the culvert itself to create a tumbling flow and then slow down those velocities. And then for the diverging culverts, we suggest, which also have roughly 12 feet per second exit velocities, we suggest using 18-inch stone riprap. And that was found using the COSA Stormwater Design Manual. This graph shows that whenever you plot 12 feet per second, it is recommended that we use 12-inch stone riprap, but for the more, to be on the more safety and resilient side, we chose that 18-inch stone. So going back through and modeling the entire system into HEC HMS one more time, for that 100-year storm event, we have that north catchment, which produces that 225.1 acre feet of water. As it enters into the detention pond on the north side of our park, 157.2 acre feet is diverted into the river. The remaining 67.9 flows through the West Harris Avenue culvert, and then from there, 55.1 acre feet is diverted through diversion 2 into the debris basin. The remaining water flows down and into the main system here, where it intersects with the west and the park catchments, and then and that creates a total pond accumulation of 86.5 acre feet. Where then it would overflow through the existing overflow culvert at 26 acre feet, or overtop the overflow dam at 58.3 acre feet. And so what this all pretty much tells us, if I knew this, is just that for that conceptual dam design, it would have to be designed to handle a flow of 152.7 cubic feet per second during a 100-year storm event. And now, Chadwick will be talking about the water treatment process.
So now we have a water treatment and water reuse overview, and we have a process flow that follows, and this process flow will basically, in summary, tell us what we're doing here. So we have a stormwater pre-treatment, and we'll be removing most of our trash and debris to have better high quality stormwater entering into our stormwater storage. And then we'll be pumping some of the water from the stormwater storage into our reuse storage tank. And for the reuse storage tank is basically to, offset the park's part of the water demand. And then if we cannot pump any water from our storage, we'll tap into the city water, and then we'll connect to the existing parks, existing irrigation system. Okay, so for the stormwater pre-treatment, we have a treatment train of the trash rack, forebay, and wetland. And here we have a profile view of what's happening at the West Harris Avenue culvert. And this profile view shows the trash rack where we be removing most of our trash debris, and then that stormwater will outflow into our sediment forebay, where those core sediments will then settle. But if we have high storm events, most of the debris will enter into the divergence culvert that Griffin talked about and go straight to the existing debris basin. And then whatever sediments that goes into the wetland shrubs, the wetland treatment, those will be removed by the stormwater wetland will help to absorb the nutrients and pollutants that comes with the stormwater to improve the body. So going through the treatment train one by one, the first on the list is the trash rack, and the trash rack is basically to collect large debris like tree limbs and stuff like that. And it will also protect the downstream systems that I talked about, like the forebay and the wetland. And it will make the trash rack will also make the maintenance and debris removal much more easier because we can easily locate where those debris will be. So right here, we have two options for our trash rack system. We have the vertical trash rack, and we have the incline trash rack. The difference between them is that for the incline trash rack, when debris accumulates, it will follow that incline. So as the water level elevation goes up, the debris will also go up with it, compared to the trash rack, the vertical trash rack, where debris will basically just settle at the front, and that would cause a huge maintenance issue. So we propose going with the incline trash rack because we want to keep that trash from basically blocking the front of the culvert, and we want to make maintenance as smooth as possible. Here we have the trash rack locations. The trash rack location at the north and at the west part of our site, and we have existing pictures of what those culverts look like, and then I made a AI generated image to show what the proposed incline trash rack would look like at that location. Then for our second phase of the treatment training, we have a 4-bay. And the 4-bay is basically to increase flow velocities and capture as much porous sediments and debris. And it also simplifies the maintenance by collecting sediment in one area. So we have an illustration here from the Rhode Island Stormwater Design Installation Standards Manual that shows how we are planning to design our 4-bay. So our 4-bay will have side slopes 3 to 1, and they're typically at a depth between 2 feet to 4 feet. And it's bottomed with concrete or grounded storm or grounded foam banks. And then that water would go through a spillway and enter into the next pre-treatment system, which is the stormwater level. So for the stormwater level, wetland, it slows and stores runoff, and it removes pollutants from the water. It removes pollutants from the water by absorbing the nutrients and the phosphorus. These things can come from lawn fertilizers or pet waste, and it will basically absorb all of those finer pollutants that can't really be seen with the naked eye. And here we have some wetland shrub options. All three wetland shrub options, the buttonbush, the wax myrtle, and the Virginia sweet fire, all of them are seasonal tolerant, so they can handle dry periods and wet periods. But for our selection process, since all of them are capable of handling dry and wet seasons, we wanted to make the park aesthetically pleasing by choosing one that would, beautify the park. So we have the wax myrtle, which is just a plain wetland shrub. There's nothing really exciting about it. And then the Virginia sweet spire has this long white blossom that brings a fragrance to the park. And then you have the bush that has a spherical blossom that brings pollinators such as that it attracts butterflies to the park also. So we chose the bush over the Virginia sweet spire, and the reason why we chose that is because the Virginia sweet spire, even though it's seasonal tolerant, it thrives in wet soil more. So we went with the bush because it's seasonal tolerant, it's aesthetically pleasing to look at, and it also brings pollinators and butterflies to the park also. Now let's talk about storing that stormwater that the treatment train has worked so hard to improve the quality of the water. And we are recommending an aerated retention pond. And the reason why we recommend an aerated retention pond is because bringing oxygen to the water improves the water quality and reduces odors, and it also circulates the water to prevent stagnation. And if the water is stagnant, that will cause algae to form, and we don't really want that for our storage pond. So the aerated retention pond not only provides treatment, but it also provides an aesthetic look for the park as well. And remember that we'll be using our storage pond to withdraw some of that water for irrigation reuse. So here we have a cross section that shows where everything will be placed, such as the geomembrane pond liner, which we'll talk about soon. And also we have the overflow culvert, which our pond can take 5 feet of water, can store up to 5 feet of water, and we plan to withdraw 2 feet of that for irrigation purposes. But if we do have a high flow storm event, the excess water will go into the overflow culvert and then transfer itself into the existing debris basin that we've been talking about. Now, for the money maker part of the project, the supply and demand. So after collecting the park's water bills and analyzing it, we realized overall that the park uses 35,000 gallons of water per day. But that 35,000 gallons per day also includes both irrigation demand and also what they use for the water use. So the specific irrigation demand that they use daily is 12,000 gallons, right? And remember that I talked about you can only withdraw 2 feet of that water from our storage pond. So if you withdraw 2 feet of that water, we get about around 260,000 gallons of water if we withdraw that. So for the irrigation demand offset, we have an average annual rainfall event of 17. The average rainfall event is basically the amount of rainfall that we get to fill that pond level back up to the 5 foot level mark. And if you multiply the 17 by the almost 260,000 gallons, you get an annual water produced by 4.4 million gallons of water. So if you look back over here, the irrigation demand for the park annually is 4.3 million gallons, but we produce almost 4.4. So on the annual irrigation demand we met is 102%. So we have a surplus of water than what the park requires for irrigation purposes. And they would say 24.4% from the park's annual potable water usage that they get from the city.
So these two slides kind of go hand in hand. What we wanted to know was how the pond water levels will actually fluctuate over time. So to do that, I modeled everything back into EPA stormwater management model, working under the assumption that that concrete dam has been replaced, as well as the pond liner, so we don't have any seepage or infiltration. And then we uploaded data from the past 10 years of daily rainfall data in San Angelo. And what we also ended up finding is that our optimum pond water level is that 5 foot, like Chadwick was saying, and then the minimum aesthetically pleasing pond water level is 3 feet. And then based on all this data and some modeling, we found that the pump flow for that irrigation is best around that 10 gallon per minute mark. And if it was to be pumping continuously, it would take 18 days to pump out that 2 feet of drawdown, which is at 258,000 gallons of water. So putting all that into the software, we get this graph on the left, which is great. What this is showing is the past 10 years of data based on that rainfall, how this pond water level would actually fluctuate. And so what's happening is it's starting at that 5 foot optimal mark, it's drawing down 2 feet to that 3 foot mark, and then that's where the pump shuts off. And that's also, this drawdown includes the evaporation process as well. And then it fills back up during the rainfall event, which, as Chadwick said, is around, we get 17 of those per year just on average. And then it draws down again. And it does not take a lot of rain to actually fill up the storage of this pond. Just from some calculations, roughly half an inch. Yeah, half an inch of rain would do it. And then we take an average of all of that and put it into this graph here on the right. And what it shows is that the water level on average stays around 4.5 foot elevation, surface elevation, only dipping down during the dry months like in the summer. So here is what this 5 foot of water would look like inside the park itself. Everything in this blue area is where the water will be inside the pond. One thing we have to note is that this existing bridge that crosses the channel there, its bottom elevation will just barely be touching the surface of that water surface. So we recommend raising that another foot or so. And then in the west, we also have this another proposed forebay, which we had already talked about what was going on in the north. For the west side, what's happening is water's coming out of this culvert and flowing straight through the channel and into the system. But we want sedimentation to occur in that area, so we propose lowering the elevations on the backside here so the water has time to accumulate in that forebay itself, have that time to sedimentate before flowing into the channel as it starts to grow in excess.
this is what our pond would look like at the 3 foot, mark. I just wanna quickly point out that there's a wetland right here, but there's no wetland in this channel right here, and the reason for that is because since Griffin mentioned that most of the water is coming from the north inlet, we decided to maximize on the amount of free treatment systems that we could put here instead of putting a wetland right here at the west here. It's not really needed because it doesn't see as much as the water that is coming from the north side. And now for the pump selection, our selection parameters include, as River mentioned, we need a pump that can pump 10 gallons per minute, and it's going to be pumped through 2-inch PVC size pipe, and it will have a total dynamic head of 45 feet. Total dynamic head is basically the pressure that the pump has to overcome to bring the water from its source all the way up to its destination, and it should have a net positive suction head, NP SH of 15 feet. The net positive suction head is basically the absolute pressure at the pump's suction inlet. So when the water goes through the impeller, there's no vapor bubbles there. So over here we have a performance curve from this pump brand, Goldwoods pump brand, and when we plot all of our data onto the performance curve, it basically tells us that we need to choose this brand of a pump, the HSC07. So that's the pump that we chose. And it's a 3/4 horsepower single phase motor, and the maximum flow that it can produce is 45 gallons per minute, and it has a maximum head of 122 feet. And it has a closed coupled design and it's sufficient for pressure boosting. And what's good about this pump is that we can also throttle it to lower the maximum flow or increase it if necessary. So for the reuse storage tank, we have 3 options. We have a plastic tank, an underground fiberglass tank, and a galvanized steel water tank. For the plastic tank, it's easy to install, it's corrosion resistant, but the downside to it is UV exposure makes it less durable over time. For the underground fiberglass tank, it saves surface space, so because you can save surface space, you can basically add as big as of a tank that you would want to. And it's also corrosion resistant, but because you're going to have to excavate to put it underground, it's going to have higher upfront cost. And then lastly, the galvanized steel water tank, the galvanized zinc coating makes it, gives it the corrosion protection, and it's cost effective and it's commonly used. When you do rainwater harvesting tool, they typically use galvanized steel tanks to do this. So we ended up choosing the galvanized steel tank, steel water tank option because of all of these pros. So, as I said, this is a park, and just like the wetland, we wanted to provide an aesthetic look, and the way how we provided this aesthetic look is to do this masonry, enclosed masonry facade at the galvanized steel tank, and this is where it will be located in the park. It's just behind the statue that they have right at Lloyd Street, Lloyd Park Street, and the tank size is going to be 35,000 gallons. And the reason why the tank size is 35,000 gallons is because we want the park to have at least 2 to 3 days of irrigations that they can get from this tank. Now, do we need to treat the water again before it's connected to our irrigation system? And the answer is it depends. If we were connected to a sprinkler system where it's more exposed to the public, we'd have to treat it for disinfection, we have to reduce the turbidity, and we have to reduce the iron. But since we are connected to the park's existing drip irrigation system, we don't have to do any treatment. So that saves a lot of money because you don't have to add any additional treatment processes. And this information I got from the stormwater harvesting guidance document for Texas Water Development Board. I know, as I mentioned about the supply and demand, we produce a surplus of water for the park's irrigation demand. But if you were to tap into the city water, you have to follow some codes when you're doing so. And one of those codes from the TCEQ, the Texas Commission on Environmental Quality, we have to have a backflow prevention system so that that stormwater doesn't backflow into the city water. And here's a standard detail of this, where there's an air gap between the tank and also the portable water supply, and it should be that air gap should be a minimum of 1 inch, and then you have the overflow rim and an overflow pipe. So if there's an overflow, it would go into the overflow pipe, and then you have a separation between the portable water supply and also our non-portable water system, which would be our stormwater harvest. And now moving on to the last thing is the connection to the existing system. Now, to connect that, to connect the stormwater from the reuse tank to the existing drip irrigation system, you need a booster pump. Now, we haven't really sorted out where we would be connecting to, but nonetheless, we would still need a booster pump system, and we recommend the Blackford CMB 1-44 booster pump. It's a similar pumping system to what is being used at the Kirby Park. And then when that water flows through the booster pump, it will go to a disc filter, which will also remove the fine particles and debris. And because remember, for the drip irrigation system, the piping is very small, so we want to filter out all of those fine debris before it's pumped into the fine drip irrigation line.
So going into some of our conceptual designs, the first one we're going to be starting off with is the retaining wall. The current retaining wall at the park has a bunch of erosion damage, and it's seeping a little bit as well with some of the cracks that are in between the stone masonry. So what we recommend is a cantilever retaining wall, which is basically an L-shaped reinforced concrete retaining wall. And to match the aesthetic of the park, we plan on using a lot of the old stone masonry that's on the original retaining wall for the new retaining wall, just to keep with the aesthetic of the park and keep with the historical aspect of the park as well. And the total area of the retaining wall is about 5,120 square feet. As Griffin mentioned, this is the current state of the bridge, and the water is at the 5-foot level for the lagoon. What we propose is raising it a foot, that way we have a little bit of clearance underneath that bridge, so it's not always sitting on top of that water. And then moving on to the pond liner, we decided to do a HDPE geomembrane liner. In order to do this geomembrane liner, we would have to have geotextile layers for reinforcement. What we propose is having one geotextile layer underneath to prevent puncture to the geomembrane liner, and then we recommend putting another one on top. That way, when the city needs to do maintenance, they can go ahead and get their equipment in there and scoop all the sedimentation or debris or anything else that gets into the pond without causing any damage to the pond liner itself. And we would need enough to cover roughly around 17,350 square feet for that pond. And as you can see down here, the pond liner will stretch all the way from the berm, separating the wetlands from the pond, all the way over to our proposed concrete dam. And for the dam, we propose a concrete dam, basically just replacing the concrete dam that's already there. The reason for this is that it has a high strength and high durability, and it can have a long-term design if designed properly, anywhere from 50 to 100 years for a typical concrete dam. It has a high water retention, which is what we're going for. We want to keep as much water in the lagoon as possible for our stormwater reuse and for aesthetic purposes. And then it safely handles the 100-year storm flood conditions, and it can be designed as an overflow design, which is what we're needing for when the lagoon has too much water and the divergent coverts or the overflow coverts can't handle that. So this is our overall proposed system layout. As Griffin mentioned, we have our detention pond up here with our divergence 1. Flowing through that culvert, we have our forebay, our wetlands, and our entire our lagoon. And then we have our bridge right here that we propose raising a foot so it doesn't touch the water. We have our forebay over here leading into our lagoon, our overflow culvert going into our debris basin, and then the rest of it flowing down to our proposed concrete dam. And as you can see here, this is where we're genuinely wanting to put the proposed galvanized steel tank. Any questions?
Were you gonna leave a bridge or a walkway over the dam? How much will this cost?
Roughly 5.6 million in total. We have 4.7 for the hydraulics, and then 410,000 for the water treatment system.
Can we go back to the project overlay?
The what?
Project overlay. So, you said you have a little wetland system up there, right? And the shrubs you're using are like dry season and wet season resistant? But what happens if we get to like a severe drought?
That's why it's very appropriate to choose the right, wetland shrub option. So the bush can handle those extreme dry conditions.
And then you said that you had it covering mostly the north side and not that Fort Bay part? Does that?
Over the west?
Yeah.
And the reason why it's not, at the west, side of the site is because we wanted to have a more pre-treatment system at the north, so that, because there's more water coming from that side, so it wasn't really necessary to put it, it wasn't necessary to excavate that channel of water just to add wetland.
Does the lily pad provide any kind of water treatment?
No, so the west is only from this culvert that's going down.
But where does the water lily pond water goes eventually, or is recycled?
I think there actually is an outflow right here that connects to that Fort Bay.
Would that water be cleaner or dirtier than?
That comes straight out of city water supply, goes into the ponds, and then drains out into that area right there. It's a very low flow of water.
Can you go back to the cost? And then, did you consider bentonite clay in the pond as opposed to, till then, as opposed to using the HDPE pond liners?
No ma'am, we did not look into that.
Griffin, hey, great presentation, guys. Just had a quick question. So on y'all's new proposed, or the elevated bridge, was there any consideration of just, going back with a new bridge? I don't know how feasible it would be to raise that existing structure since it's just kind of old, and I don't know what kind of issues might go into that, but.
Is it a sword bridge right there?
It's not designated for, but there's a lot of emotional attachment to that bridge.
Right.
Especially on teenagers early in the morning.
Our goal is try to keep as much of the historical elements that we can with the park, and that bridge was one of them. Later on, if they decide to replace the bridge for a new one, then that would be their decision, but as of right now, we're just proposing to keep it and raise it.
Thank you. Yeah, great job on the presentation. I was wondering, did y'all consider anything else other than 4x4 box culverts, like doing open channel versus?
So, yes, sir. We can do, we consider a couple different things. The only thing about the open channel was just that sanitary sewer utility, and we just didn't want to leave that open. So we wanted to go with the culvert. And we tried smaller culverts initially with one barrel, circular concrete culverts, and it wasn't cutting it. We just have so much water coming in from the north at a flow rate of 550 cubic feet per second. There's not a lot of things that can actually handle that. And it does seem like overkill for that 2-barrel 4x4 box culvert, but it was the only thing that could actually handle that kind of flow.
Did you look at the impacts of the Concho River and then all that water into it perfectly?
That's where the energy dissipation. question to piggyback on energy information. Is there any consideration with the retrofit internally, how that would affect the user stream? No, sir.
So instead of building a box curve culvert, could you consider releasing the water on the north side directly into the river instead of running into the whole box?
So it's already running into that detention basin just from the house. So the high school is flowing it directly into that detention basin.
Is it surface flow or is there storm sewer around?
There's storm sewer that runs through the high school, under the parking lot of the high school. And then it crosses. Yes, sir.
Another question. So during your research in PCQ, was there any permitting that you needed as part of the, using that?
Yes, there was permitting.
What about, long-term maintenance? I know this area is kinda hard to get to, you know, to make it easier for the city to be able to get down there. Is there accessibility that I'm not aware of?
Yes, sir, there's accessibility.
The code currently
But go
has
back to the
ramps.
overview and show them what's that.
So there's, an accessible point right here into the actual pond system itself. There's also one right here. And then for the debris basin, where they can actually come in, there's one right here.
Is this in the flood one?
Yes, sir.
Which one? Comment, then another comment and question. I know earlier on y'all were looking at having 4 bays of both inlets. And then you decided to go just with one at the end. You're still showing it here on this slide. I thought we were talking about not having 4 bay there. Is that
No,
correct?
we're gonna have 4 days at both locations.
Just not the wet.
Just not the wet.
Okay. That, were you talking about, there was a channel underneath that sewer line that goes north of Harris? Remember earlier?
Go back to the cross-section with the existing sanitary sewer here. You went over that, but it wasn't clear what you were trying to say. That's what he's asking.
So,
Yeah,
so
that-
do you think, you said that there seemed to have been a natural channel there before?
Yes, sir.
Show them where the original ground
This is where
surface.
the original ground and surface elevation is, this line right here, it dips. And then during construction, they put a fill all over that.
Okay. Do you think that was like a natural channel in the past? Okay.
Was
So
that
how high is that from the river? The bottom of that, how high was it from the river?
The bottom of this is right at the 18 or 22. So that's around 8 feet above the river.
Okay. And what is this other dip here?
This is actually on the other side, so what's happening, this line set was a little confusing, but this, it's running, this sanitary sewer runs over here, and then it goes across the bridge in this direction. So what's happening is, the sanitary sewer is running right here, and then as it goes across that bridge, this is the new, station.
So that's actually the river
Yeah.
channel.
So this is the river right here.
So where,
That's part of the river.
in the color image, in the color image above, can you kind of point where you think that natural channel ran?
Probably right around this location.
Is it like going east-west?
Yes.
Okay. You might have solved the mystery.
Yeah.
I remember reading an article from the Standard Times or from the Standard from 1895. It mentioned some waterfalls along the Conway River that was around the bend. I have kayaked up Sulphur Draw, but there are waterfalls like this, so I didn't think that was it, and it's at the bend. And so I assumed that there were referencing the location here, so that might have been the location where there were waterfalls. And that ties in with all the water that's flowing into that north end. So if there was a natural channel that cut that way, that might have been what they were referring to. It's unfortunate that all the developments did away with that.
Well, the project would restore the waterfall though.
And that also ties into that north side of the park. That north side of the park was park property until Harris went through.
So was there consideration to be able to fill river, and if it's meant to be aesthetically pleasing, it will dry up at some point with their consideration to keep water in it when it's not raining.
For inside the lagoon, oh, yes, sir, so that's what, there's actually retain water inside the lagoon.
But the river, like if you don't have a rain event, is there an alternative way to get water in there?
Oh. So, but, I mean, it doesn't take a lot of rain to build up. I mean, unless there's an extreme drought, with this plan, it shouldn't drop below 3 feet in a certain spot.
Are these elevated to where they just activate during a certain storm event?
Yes, sir. So the Divergence 1 is elevated 3 feet higher than the West Terrace. And so during like once we get those higher storm events, that's when that will actually start to.
You have an idea what storm events starts activating?
We'll start activating pretty much around 2 years, 5 years.
Okay. And I'll piggyback on that, since your low flow can create a lot of your debris up, was there any consideration, so if you get there, kind of keep that trash from going out the roof? Ruben, what was your process for determining your disciplinary area? Like what software?
Also use ArcGIS for using a digital elevation model, and then that has a bunch of visual analysis tools, like a fill model or water accumulation model. And then overall, it ended up generating this image.
Probably got time for one more question before I get the last question.
How surprised are you when you deleted that and saw 500?
Yeah.
And I wonder if you're going with the river rise above the culvert, if you check the water level in the river.
We're coming out at a higher elevation than the river by like 7 feet or so.
But you didn't check that.
No, sir.
So my last question is, what did you learn on what did you each learn on this project? Besides how to do stormwater management and water recycling?
Don't go into areas of engineering you're not competent in. And that just comes from, I knew nothing about hydrology before I took this.
You now, right?
Yes, sir.
Did y'all do any coordination with the local group, Art of Uncommon Places, to see if they could do anything with the galvanized steel tank?
It was an idea, but it was never, we never reached out to get that involved.
What did the other two students learn? Anybody?
Well, what I learned is, to whatever issues we have, we just put our differences aside, we just overall just take the project. That's what I learned.
Oh, you had some?
Yes.
Mine would be to not, go off the deep end with design. If it says conceptual, stick to conceptual, don't try to do more than what the what you're actually needing.
Well, thank you all very much. Appreciate it. We have three more presentations this afternoon. They're all in the mechanical engineering area, and they start at 1, 2, and 3. Thank you all very much for coming. And it's great to have you. Oh, okay. So if you're coming back to later ones, we have the large room to do those in. And please fill out your critiques on the presentation that you can give them to Lily on the way out. Thank you very much. All right, how do I tell this thing to stop?